Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I'm your host, the Dabbling Doggo.
I dabble.
Last week, we learned about the relationship between variables, expressions, and memory, and then we learned about some different data types in Julia. Now that we have a foundation in data types, let's take a look at how Julia handles those data types in data structures. Today we'll take a look at 4 different data structures used in Julia: dictionaries, tuples, named tuples, and arrays. I'll show you how to construct them and how to access them. We'll also explore some of the pros and cons of each data structure, so you'll have an idea when to consider using them. We're going to be spending all of our time in Atom today, so let's just jump right into it. A data structure is a particular way of organizing, accessing, and manipulating data. A dictionary is a flexible way to handle a lot of different types of data. It is noted for its use of a key-value pair to store and retrieve data. Let's take a look at how to construct a dictionary. This initializes an empty dictionary. DICT is the dictionary constructor. Notice that a dictionary is also a data type. In Julia, data structures are a more sophisticated data type that contains an arbitrary number of elements. These elements may be made of different data types. Remember the data type any from last week? Here's an example when Julia uses the type any as the default data type. This reads that D1 is the type DICT containing elements of type any. Here's the syntax for adding some data to your new dictionary. In this example, the strings A, B, C, and D are called the dictionary keys. The integers 1, 3, 5, and 7 are called the dictionary values. The equal to greater than syntax is called a pair constructor and is used to pair the dictionary keys on the left side with the dictionary values on the right side. Notice that the entries in your dictionary are not necessarily in the order in which you type them in. That's because data is not stored sequentially in dictionaries. You can display your dictionary by typing in the name of your dictionary. In this case, it's D1. Notice that D1 is still of type DICT, but it is now composed of data of elements of type string and of type int64. You can look up individual entries in your dictionary by using square brackets immediately following the dictionary name and entering one of your keys within the brackets. You can change the value stored in any of your keys. In computing, if an object can be changed, it is said to be mutable. Dictionaries are mutable. Now take a look at your dictionary to see how it's changed. You can see that key A has been changed from 1 to 10, and key E has now been added as a new entry to your dictionary. Notice in the workspace panel that D1 is listed in a collapsed state. You can expand the dictionary in the workspace by clicking on the arrow that looks like a greater than sign. Also notice that when you hover your cursor over the red column, D1 is identified as type DICT containing data of type string and type int64. Julia has some useful built-in functions to assist you when using dictionaries. Before we take a look at them, let's set up a couple more dictionaries to get some practice. This will list all of the keys in your dictionary. This will list all of the values in your dictionary. This will merge separate dictionaries into one dictionary. If there's a conflict, Julia will keep the key listed in the last dictionary entered. In this case, D2 and D3 both have a key called A, so the merge function keeps the A key from D3, which has a value of 100. You can see in this example, the merge function kept the key and value for A from D2, because D2 was the last dictionary entered. The function pushBang adds a key-value pair to a dictionary. Here, the exclamation point is called a bang, so it's read pushBang, and it signifies that a mutation is permanent. You can see that the key G with a value of 350 has been added to dictionary D3. PopBang permanently deletes a key along with its value from a dictionary. In this case, Julia removed the key B along with its value 30. You can see that dictionary D2 no longer has a key labeled B. Note that all of these changes are being tracked in real time in the workspace panel. So far we've only looked at small examples, but it's conceivable that you might be working with very large dictionaries containing a lot of data. So here are some tools to help you look up entries. This will check dictionary D1 to see if there is a key called A. This will check dictionary D2 to see if there is an entry with a value of 2. Dictionaries are nice because they are flexible and mutable. Almost anything may be used as a key, and almost anything may be stored as a value. The values are mutable, so you can change them as your needs change. However, dictionaries are not indexed, meaning there's no way to select an individual entry by an index number, or sort the data, or to select a range of data. Let's take a look at another data structure that does allow data to be selected with the use of an index. A tuple, or tuple, either pronunciation is acceptable, is a very efficient way to collect and index data of any type. Let's take a look at how to construct a tuple. Before we begin, enter exit to start a new session in Julia. Don't forget the parentheses. This initializes an empty tuple. Unlike a dictionary, there's no need to enter a keyword before the parentheses. You can see that TP1 is of type tuple. When creating a tuple, it's important to put a comma immediately following the value, even if there's only one entry. You can see that TP2 is of type tuple, with an element of type int64. If you don't include a comma, Julia thinks you're just setting up a new variable and not creating a tuple. So if you want to use a tuple, don't forget the comma. You can populate your tuple with entries of any type. You can see that Julia has no problem keeping track of all the different data types in this tuple. You can display your tuple by typing in the tuple name. When you created your tuple, each value was assigned an index number in the order that you entered them, starting with the number 1. You can retrieve the value or values of your tuple by using the square brackets. You can use the keyword end to display the last element in your tuple. You can enter in a range of numbers by using colon. This will give you the elements 1, 2, and 3. This will give you all of the elements starting at index 3 and going to the end of your collection. This will give you all of the elements starting at index 2 and going to the second to last element. This will give you all of the elements starting at index 1 and going to index 5, but skipping in increments of 2, or in this case, indices 1, 3, and 5. Julia is designed to use one-based indexing, meaning the first element of an index collection of data begins at 1. To an uninformed amateur like myself, this may seem natural and uncontroversial. However, it should be noted that many programming languages are designed to use zero-based indexing, meaning the first element of an index collection of data begins at 0, and not at 1. There are a couple reasons why programming language designers may choose to start counting at 0 rather than 1. The first is technical, the second is philosophical. In your computer's memory, the first element of an index collection of data is stored at a memory location. Let's call that location P, as in pointer. The second element of that index collection is located in memory location P plus 1. The third element of that index collection is located in memory location P plus 2, and so on. From your computer's point of view, the index number is not referring to the actual element of the index collection, but rather to the offset from the memory location of the first element. Did you follow any of that? The non-technobabble version is that zero-based indexing is easier for your computer. Other than the technical reason for using zero-based indexing, there are plenty of real-world situations where it makes sense to start counting from 0 rather than 1. For example, ask yourself, what time is it? Do you measure time starting at 1 or at 0? Without even realizing it, we start counting time at 0 and not at 1. So who's right? Should computer programming languages start counting indexed data from 0 or from 1? Unfortunately, this is one of those unanswerable questions, since there are times when you want to start counting from 0, and other times when you want to start counting from 1. While it may make sense both technically and philosophically to use zero-based indexing, the reality is that it's more difficult for humans to understand zero-based indexing. If you're designing a new, high-level programming language that's meant to be easily accessible for a wide range of humans, you have to consider using one-based indexing. The designers of Julia have decided to use one-based indexing, which, in my opinion, makes Julia a lot easier for beginners to learn. Alright, now back to the tutorial. You can unpack the elements of the tuple and assign them to separate variables. Note that A, B, C, D, and E are all listed as separate variables in the workspace. Unlike dictionaries, tuples are immutable, meaning that after you set them up, you cannot change them. However, you can concatenate them with other tuples to form new tuples. This example creates a tuple made out of tuples. This shows that TP7 is of type tuple, containing 2 tuples, each containing elements of type int64. This may or may not be what you are looking for. If you only want the individual elements of your new tuple, you can use what is called the splat operator to unpack the tuple. The ... is called the splat operator, and it unpacks a tuple into individual elements. Just in case you think I'm making this up, you can type in question mark in the prompt to bring up the inline help and type in ... Here's how you can perform basic math using tuples. Julia comes with a built-in function called sum, so it's easy for you to add up all of the elements in your tuple. Now, what if you want to apply an operator to every element in the tuple? For example, what if you wanted to add 10 to each element of TP9, or multiply 10 to each element of TP9? So that's not going to work. That's not going to work either. Fortunately, Julia's got you covered. You can use a built-in function called broadcast, which allows you to broadcast an operator over a collection of data. The broadcast function has a special shorthand syntax, so rather than typing in broadcast, all you have to do is include a dot immediately before the operator. This adds b to each element of tuple TP9. This multiplies b to each element of tuple TP9. Here are some useful built-in functions for tuples. This gives you the number of elements in a tuple. This gives you the minimum value in a tuple. This gives you the maximum value in a tuple. And this gives you the minimum and maximum values of your tuple. Here are some additional tools to help you navigate tuples. Imagine that you have a very large tuple, and not this small example. If you want to check to see if an element is included in your tuple, you can use the keyword in. Alternatively, you can use the Unicode in. To check if an element is not in your tuple, you can use the Unicode not in. Here's a practical application of how to use tuples. 100 degrees is the boiling point of water in Celsius, and 212 degrees is the boiling point of water in Fahrenheit. How would you swap the values of x and y so that x equals 212 and y equals 100? Well, that didn't work. X and y are now both 212. We learned this in the last tutorial in the section about variables in memory. Let's reinitialize the variables x and y. That worked, but we had to create a new variable called interim. Is there a more efficient way to solve this? Let's reinitialize the variables x and y. Using tuples allows for a very efficient way to swap variables. Simple, right? Look at the workspace for x and y as you up arrow and enter. Julia also has a data structure called a named tuple, which is like a hybrid of a dictionary and a tuple. Before we begin, enter exit to begin a new session in Julia. Here's how you create a named tuple. You can see that NTP is of type named tuple. Like a dictionary, a named tuple is noted for its use of a key-value pair to store and retrieve data. However, unlike dictionaries, pairs used in named tuples are constructed using just an equal sign, and not using the arrow pair constructor. Also, unlike dictionaries, the keys in a named tuple are stored as type symbol. We'll see this in a few minutes. You can display your named tuple by typing in its name. With a named tuple, you have more options available to retrieve your data compared to a standard tuple, but with some limitations. You can use square brackets and index like a standard tuple. So far, named tuples behave just like a standard tuple. Now try this. Unfortunately, you cannot use ranges with named tuples. When using the square brackets, you can index by using the key symbol. Note the use of the colon before the key. Or you can use a dot immediately followed by the key to index without using brackets. Here are some useful built-in functions for named tuples. This lists the keys, value types, and values of the named tuple. This lists the keys of the named tuples. This lists the key-value pairs of the named tuple. As promised, a named tuple is kind of like a dictionary, but not really, and it's kind of like a tuple, but not really. The final data structure that we will discuss today are arrays. Like dictionaries, arrays are immutable, and like tuples, arrays can be indexed, so it's the best of both data structures. In math, there's a distinction made between a scalar, a vector, a matrix, and a tensor. In Julia, these are all included in the data structure called array. A Julia array can be a single element, like a scalar. A Julia array can be a one-dimensional collection of elements, like a vector. A Julia array can be a two-dimensional collection of elements, like a matrix. And finally, a Julia array can be a collection of elements in an arbitrary number of dimensions, like a tensor. Let's take a look at some examples. Before we begin, enter exit to start a new Julia session. Arrays are created using square brackets. This initializes an empty array. You can see that A is of type array. That 1 means that by default, A is a one-dimensional array. If you look at the workspace, it's actually listed as a vector. This is an example of a scalar, which in Julia is a one-dimensional array with one element. Note that in the workspace, a scalar is called a vector because it's a one-dimensional array. This is an example of a column vector, which in Julia is a one-dimensional array with one column that contains an arbitrary number of elements, in this case, 3 elements. This is an example of a row vector, which in Julia is a two-dimensional array with one row that contains an arbitrary number of elements, in this case, 1 by 3. Note the 2, meaning a two-dimensional array. Look at the workspace. RV is listed as a 1 by 3 array and not a vector. Also, the icon in the red column is different to indicate that it's a multi-dimensional array. In Julia, the first number of a multi-dimensional array is the number of rows, and the second number is the number of columns. Also note that in order to create a row vector, you entered in the elements separated with a space and not a comma. This is an example of a matrix, which in Julia is a two-dimensional array with an arbitrary number of rows and an arbitrary number of columns. In this case, the dimensions are 2 by 3, or 2 rows and 3 columns. Note that the elements within the row are separated by a blank space, while the rows themselves are separated by a semicolon. Rand is a built-in function that generates a random number between 0 and 1. I'll discuss the rand function in a little more detail later in this tutorial. For now, we can use it to generate arrays with elements of random values without using square brackets. This generated a 3-dimensional array with 4 rows, 2 columns, and 3 layers. Look at the workspace for all of your newly created arrays. Like dictionaries and tuples, arrays can contain elements of any data type within the same array. For one-dimensional arrays like scalars and vectors, you can look up an element in those arrays by using square brackets, immediately following the name of the array, and entering in an index number. There are a couple ways to index a two-dimensional array. For two-dimensional arrays, the first approach is to enter a row-column pair separated with a comma within the square brackets. This gives you row 1, column 2. The freestanding colon means every element. This gives you all rows, column 3. This gives you row 2, all columns. This gives you rows 1 and 2, and columns 2 and 3. The colon in between numbers means a range of elements. This gives you the last row, all columns. This gives you all rows, last column. An alternative approach is to enter a single number within the square brackets. This will give you the element at the index relative to the length of the array. Before you use this approach, you need to be aware that Julia is column major ordered. What does that mean? It means that the sequence of elements start at row 1, column 1, then goes to row 2, column 1, and so on until it reaches the last row of column 1. Then the sequence goes to row 1, column 2, and follows this sequence in a zigzag pattern as shown in the column major order diagram. This shows you all of the elements in your array in the sequence that it is stored in memory, regardless of the shape of your array. Like dictionaries, and unlike tuples, arrays can be mutated. Let's use array M for this example. This changes row 1, column 2 from 3 to 9. Basic math using arrays is similar to basic math using tuples. Like tuples, you can use the broadcast function with arrays. Here are some useful built-in functions for arrays. This shows the row by column dimensions for the array. This shows the number of elements in the array. This shows the element type in the array. This shows the minimum value in the array. This shows the maximum value in the array. This shows the minimum and the maximum values of the array. This transposes the array so that the first column becomes the first row, and the second column becomes the second row, and so on. Using the apostrophe key is a shorthand syntax for the transpose function. This reshapes your array into 3 rows and 2 columns, but unlike the transpose function, the reshape function keeps your array in column major order. None of these functions cause permanent changes. These functions are for column vectors only. This displays your array in reverse order. The sort function is not permanent. If you want to permanently mutate your column vector, you can use the bang syntax. This will permanently sort your column vector in reverse order. This added 5 to the end of your column vector. This deleted the last element in your column vector. Finally, here's some built-in functions that will help you populate arrays quickly. This creates a 5x5 matrix of pi. This creates a 3x5 matrix of zeros. This creates a 6x4 matrix of ones of type float. This creates a 2x8 matrix of trues. This creates a 7x8 matrix of falses. Here are some additional tools to help you navigate arrays. Imagine that you have a very large array, and not this small example. If you want to check to see if an element is or is not included in your array, you can use the following. This is read, is the value 1 in array A? Alternatively, you could use the unit code for in. This is read, is the value 1 not in array A? This creates an array with the unique elements of A and B. This creates an array with the common elements of A and B. I know that this is a lot of material to absorb, but with practice you can do it. You can do it! For me, this is not intuitive, so I had to play around with a lot of different examples before I started to get the hang of it. Practice, practice, practice. It's possible to create arrays out of arrays. However, you should note that there's a difference when using the comma versus the semicolon. Before we begin, enter exit to start a new Julia session. Using a comma here gives you an array of arrays. This may or may not be what you are looking for. Using a semicolon here gives you a vertical concatenation of values in the arrays. This is probably what you are looking for. Using a semicolon is the same as using the vcat function. Using a blank space here gives you a horizontal concatenation of values in the arrays. Using a blank space is the same as using the hcat function. Before we begin, type in exit to start a new Julia session. Let's discuss memory again. Remember from last week, we learned that variables are storage locations that contain a value, and the value only changes when we tell it to change? In this example, A changed to 2, but B stayed at 1. This is what we learned last week. With numbers, B equals A means take the value stored in location A and place it in location B. For numbers, A and B are separate memory storage locations. However, arrays are different. When you type in B equals A for arrays, you're creating an alias called B for the array called A. In other words, for arrays, B is not stored in a different memory storage location. Instead, it is simply pointing to the same memory location as the array stored in location A. Notice that A changed and B changed. Since B is just an alias for A, any changes made to A will result in a change to B and vice versa. If you want to make a copy of the array A that will not change if you make changes to array A, then you can use a built-in function copy to create what is called a shallow copy. Notice here that A changed, B changed, and C did not change. Using the copy function created a copy of array A in a different memory location, so changes made to either array A or array B will not impact array C. Notice here that A did not change, B did not change, only C changed. Now that we have some experience with the different data structures, let's take a look to see how much memory is consumed by a dictionary, a tuple, a named tuple, and an array. Before we begin, type in exit to start a new Julia session. Let's create a dictionary, a tuple, named tuple, and an array, each containing the same number of elements with the same values. For dictionaries, remember to use the DICT constructor along with the arrow syntax to pair the key to the value. For tuples, remember to use the parentheses and the comma. For named tuples, remember to include a key followed by an equal sign and not the arrow syntax to pair the key to the value. For arrays, remember to use square brackets. Look at the workspace for the dictionary, tuple, named tuple, and array. Hover over the red column and note the different icons and the different types. Now type in var_info. Here are some observations. The tuple and the named tuple take the least amount of memory. In fact, they're the same size, which is surprising to me. I thought the named tuple would have been a little larger than the standard tuple. The array is about twice the size of the tuple, but the dictionary is bigger than the other three combined. When trying to decide which data structure to employ for your project, here are some factors to consider. Dictionaries offer a lot of flexibility, but consume the most memory. Tuples are the most efficient, but are the least flexible. Named tuples offer a few more options than standard tuples without taking up any additional memory, but do require more keystrokes. And finally, arrays offer a balance between flexibility and efficiency, so it's a good choice for many situations. Arrays are like the Swiss Army knife of data structures. They can be used for almost anything, and they do it efficiently. Type in exit to begin a new Julia session. Before we conclude, we need to revisit random numbers and strings. I mentioned the rand function briefly earlier in this tutorial. However, there's a lot more to the rand function. The rand function generates a random number between 0 and 1 using uniform distribution, meaning that over a large sample size, the average will be 0.5, but the individual numbers will be evenly distributed between 0 and 1. This generates a single random value between 0 and 1 of type float64. This creates a one-dimensional array with 5 elements with random values between 0 and 1 of type float64. This creates a two-dimensional array with 5 rows and 5 columns with random values between 0 and 1 of type float64. This generates a three-dimensional array with 5 rows, 5 columns, and 5 layers with random values between 0 and 1 of type float64. However, you are not limited to just numbers between 0 and 1 of type float64. The rand function is a lot more flexible than that. Consider the following examples. You can select the type of element in the array by including it as the first argument. You can choose a range of integers to use by using the colon syntax. The rand function is a convenient tool to quickly populate an array of any dimension as a starting point for further analysis in your projects. Type exit to start a new Julia session. We discussed strings last week. Now that we know about data structures, we can now discuss an interesting feature about strings. Unlike other primitive data types, strings can be indexed, similar to a tuple or an array, since a string is really just a collection of characters. Let's use our old friend Hello World for this example. You can look up individual characters by using a similar syntax we used when indexing tuples and arrays. This returns characters 11 through 6 in reverse order. This returns characters 3, 5, 7, and 9. Note that S1 is of type string, and that each element of S1 is of type char. Here are some useful built-in functions that you can use with strings. Some of these are self-explanatory. This is a way to look up strings within a string. The replace function is interesting. It uses an old-new pair using the pair syntax similar to what we use in dictionaries. Here's how to convert a string into an array. This converts your string into a one-dimensional array with elements of type char. This converts your string into a one-dimensional array with elements of type substring containing elements of type string. This is the same as the previous example, except that it separates your string at a blank space rather than listing all the individual elements. Here's how to convert an array containing string elements into a string. Notice that CV4 was originally an array, and that S2 is of type string. Like tuples, strings are immutable. But here are some hacks to get around that. In this first example, try to change hello into jello and make that change permanent. So you can't do that. Instead, you can use string concatenation that we learned last week, combined with string indexing that we just learned. Or you can use the replace function that we just learned. Now the change is permanent. In this next example, try to reverse hello world and make that change permanent. So you can't do that. Now the change is permanent. Wow, that was a lot of material to cover. Today, we learned about the Julia Data Structures, dictionaries, tuples, name tuples, and arrays. We learned how to build them and how to retrieve data from them. For reinforcement, we practiced with a lot of different examples. Next week, I'll introduce the concept of control flow, which will allow you to build logic and automation into your code. If you enjoyed this video and feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you have any questions, please post them in the comments below or send me an email at julia4ta@gmail.com. Feel free to spread the word by sharing this video, since I'm sure you'll all agree that this is the finest tutorial on all of YouTube.
Worst tutorial ever.